Hi there. My name's Nash, and I'm a developer relations engineer at DataStax. DataStax is building an AI platform for you to build generative AI applications. We have two parts of this. We've got AstraDB, which is a NoSQL and vector database, and Langflow, which is a drag and drop builder for generative AI applications. I'd love if you check them both out at datastax.com. Otherwise, again, my name is Phil Nash. You can find me all over the internet as Phil Nash on any of your social media networks of choice. I'd love to connect with you. So what are we talking about today? Well, I got the motivation to talk about regular expressions from a number of emails and notifications I got from Dependabot, from the GitHub dependency updater, which used to send me a bunch about last year, sent me a load of notifications about a bunch of different dependencies of mine in applications that had ReDoS vulnerabilities. And ReDoS is the regular expression denial of service vulnerability. And what that means is you can write regular expressions that, given a particular string, will run for enormously long amounts of time. And regular expression is in JavaScript, dealing with a regular expression is a synchronous operation. So running for a long period of time means it blocks the event loop and can ultimately either block your interface in the UI or block and run up the CPU on your server and ultimately take down your application. We want neither of those things. So I wanted to talk about regular expressions and how to avoid the ReDoS vulnerability, how to spot it, and generally remove ReDoS from our lives. I was worried about this because if these are available in open source, if these vulnerabilities are in open source projects and they're being found by people looking for them, then if we've got regular expressions in our own applications, then people might also be looking for, the vulnerabilities might be there. We might not be looking for them. And so this is to give you an idea of what to look at when you're writing regular expressions and if you have regular expressions in your applications. There are a few regular expressions which I'll be referring to over the course of this talk, and we'll explain them as they come. But here's just a couple. They start off relatively simple. That one's a bit more complicated. We get to this one near the end, which is a lot more fun. But don't worry, we will break them down in order to show you how to understand them and how to understand where their vulnerabilities are. Great. So in this talk, we're going to talk about catastrophic backtracking. This is the worst possible regular expression vulnerability that you can come across. Catastrophic backtracking will allow your will cause your code to run in exponential kind of time based on the length of a string passed to a regular expression tester, and that's what we want to avoid. It's the worst possible way because it's so easy to trigger this with short-ish strings. There's other kinds of backtracking that is useful to regular expressions. It is also potentially vulnerable. But this is the worst. And this is the one we need to concentrate on the most. So we're going to start with this regular expression, which was found in the Node Fetch library. Node Fetch was an implementation of Fetch for making HTTP requests in Node to sort of match the browser version. Of course, Fetch is actually built into Node.js these days, but the Node Fetch library existed for quite a long time. And this was a regular expression that was used to test against URLs going through it. I think it was part of a header. And in this case, basically, it was just trying to test whether this URL was on localhost or not. And so either it's a string that is localhost, or that has a bunch of subdomains and other things before localhost and then finally ends up as localhost. So it's either localhost or something.something.something.localhost. Perfectly reasonable thing to use a regular expression for, maybe? We'll see. See, this was the regular expression, and it is vulnerable to catastrophic backtracking attack. Now, what does that mean? Well, if we were to run a test against it, like this, then you can actually see with your eyes right now that this test will not pass. This will not match a regular expression, will not match in the string at all. And that's because this string doesn't include the text localhost whatsoever. And so it's never going to pass. But the regular expression engine in JavaScript does not know that. In fact, it works from the start of the string. And so we have to handle that. We have to understand how it works in order to do so. And so at the start of the string, let's understand what we've got going on there. We've got this caret symbol, which means the start of the string. And then we've got this group of objects. The dot means any character. And the plus then means one or more times. And then slash dot means the dot character only. And then this entire group can be used 0 or more times. That's what the star means. And so that 0 or more times means it could be 0, thus it's just the string localhost. But the or more times will cause us issues here. And secondly, we have this dot character, which means every character possible could be matched. And so let's see how this would work. We're testing against a string with a.a.a.a, and we can see that there's no localhost at the end. Now, what the regular expression engine is going to do is apply that to the start of the string first. And it's going to apply this group to the start of the string first. And we're going to say we have obviously not 0, but we have more versions of this. But we can actually kind of greedily kind of suck up most of the string. All of the a dots fit into this pattern dot plus slash dot, because this dot plus actually matches the period to the dot character as well as everything else. And so that dot plus is matching all of these a dots all the way up to the end. And then and then we finally match this dot character as the actual slash dot. With the regular expression engine, we then go, okay, that's finally not localhost. Understand that, that's fine. Okay, but the regular expression engine is not done here. This is where it backtracks, what it calls backtracking, by looking back and saying, how else could I approach this string using this pattern? And so we then, we can go again. This time around, we're going to match 5 a dots as the first group. And then because of the star, we can have more groups of this. So a dot is the second group of it. And then we get an a at the end, and it's not localhost, and so we fail. And so we can take a step back again. We can maybe go 4 a dots, and then we can break that down into a dot, or a dot, a group of a dot, and another group of a dot. And you can see this is where things start to split up. We have this this version, this third version of the matching, is actually has 2 versions that can work, which is bad. And then we step back into this third kind of version, which we have a dot at the end, but that can also be 2 a dots and an a dot, or an a dot and 2 a dots, or 3 singular a's. And this is where it's sort of starting to increase. Every time we now step back and have more of the string to test against, the number of tests we have to do increases by 3, 4, 5, 6 times. And ultimately that goes off into exponential size and can take an awfully long time. We can actually go and check this out. We've got a couple of tools we can use to inspect this. So this is regex 101. It's really useful for testing irregular expressions and understanding what they do. And if we look at this test string in here, we can see just over here, regex 101 shows us that it doesn't match, but it's taken 12,294 steps to get there. Whilst that was only 665 microseconds, 12,000 steps is quite a long thing for a string that's only this long. And if we were to add another .a onto there, we find that now says 24,582 steps. So adding an extra .a to this string doubles the number of steps required to test it. And if we add it again, we get to 49,000 steps. We add it again, we get to 98,000 steps. And now it's taking 2.2 milliseconds. Still not seemingly a long time, but we can keep going. And ultimately, regex 101 will detect when catastrophic backtracking has taken place. Another nice place to look at this is in the debugger. It kind of halts after 150,000 steps, basically. We can look at the debugger and we can speed it up as fast as possible. And you can see all of the matching it's trying to do, where it breaks it down and it's kind of going through the end of the string so many times. And we're only on 100 steps right now, but we've only kind of reached back to 4 A's back from the end of the string, and we're still looking at them all. So it's a bad time. But regex 101, really useful little debugger for that kind of thing. And I also built this regex timer, which allows us to just test these kind of strings as well. And in this case, we can test the same kind of thing. And we can see this string has taken 3, 4, 5, 6 and a half seconds there. And again, if I add an A to that, add a .a to that, browsers do some weird caching, certainly Chrome. So this one now took 4 seconds instead of 6.5 seconds. But I think if I add another .a, probably going to take up to 8 or 9 seconds. It's confusing, but it takes a long time. Just to note, this is doing the test in a web worker so that the browser interface is locked up. But if you were to try and test this regular expression in the main thread of a browser, that's going to lock up every kind of animation, everything on screen for your users, which sucks. So regex time is a good way to explore these things as well. Let's talk about this in real world, though, with what I like to call the Cloudflare up. This was an issue that happened with Cloudflare that took down most of Cloudflare's services for an extended period of time. This was the regular expression that achieved that, and it's kind of a complicated one. So in this case, if you are dealing with complicated regular expressions, it's, I think, good to visualize them. One tool to do that is called regexper. That's regexer.com. And this kind of gives you this visualization of the expression. And we can use this to kind of break down and simplify the expression to see where the issue is. And so this first kind of column of stuff here is just a bunch of sort of JavaScript-y symbols, like we've got symbol undefined, null, false, we've got some brackets, some quotation marks. And we need at least one of these in order to match and move on. Now, what's useful about this tool is it also shows when we don't need things. And so when we get to this, we've got a bracket here and a colon here. And you can see both of these. This could be one or more brackets. It's actually 0 or more brackets. We can skip over it with that little line over the top there. And the same for this colon. It's either 0 or 1 colon, but we can skip over it and say 0. We have the same thing with this set here, some white space or other sort of bracket notations, but we can skip over it. It's 0 or more of these things. And then we get to the real meat of the issue. We have this any character any number of times, any character any number of times equals any character any number of times. That is dangerous. And so if we consider all these bits that we can kind of knock out, these three kind of sections in the middle, and if we just kind of simplify this first part by picking one of the strings to look at rather than looking at the enormously long thing, then we actually break this whole thing down into this regular expression, which is easier to look at, although it doesn't do the same thing, but fails in the same way, and that's important. And so here we have a quotation mark followed by dot star equals dot star. And our issue here is this dot star. That means any character, any number of times, twice. And much like what we saw with the node fetch localhost kind of overlapping of dot and the slash dot, because a dot is any character and it appears inside any character. Right here we have any character can appear in any character any number of times. We get permutations and permutations and permutations of the different characters that can exist here. And if this string then fails to have an equals in it, then the thing will eventually not match, but we've got a bunch of stuff to test firsthand. And so this ultimately caused a 27-minute outage on Cloudflare, which took down a good portion of the internet with it, because Cloudflare does host a good portion of the internet. For 27 minutes, it's awful. And so you can actually read up about this outage and how they dealt with it, and how it's not just a regular expression that causes this, but sort of cascading failures, and the management and the tool that you need in order to fix that when not half, but a good portion of the internet has suddenly dropped out, including your own admin panels. It was a bad time for Cloudflare. It's a bad time for their customers. But all really boiled down to this one regular expression. Just to note, I think this regular expression was used to, it was trying to detect sort of script injection. And so it was clearly being applied to a lot of HTML pages, and Cloudflare serves a lot of HTML pages. So you put one bad regular expression in the way, and you just take down the whole lot. I want to give you some other examples here around email regular expressions. The worst type of thing to try and test with a regular expression, I promise. Never try and mess with email regular expressions or regular expressions to match emails. At least don't get complicated with it. So I've got two examples of this. One's Superhuman. Superhuman are a company that build an email client so for your desktop, and it's built in Electron. So that means the interface is all built in JavaScript, HTML, and CSS. And so in this case, if you get the JavaScript in a regular expression wrong, it will end up locking up that interface, and that's bad news for your users. And so Superhuman it's an email client, so they obviously want to validate email addresses, and they started by using this regular expression. This one's perfectly reasonable. This one says anything that's not an @ symbol 0 or more times, and then an @ and then a whole bunch of other things that are not an @ symbol. And that is basically just testing that a string has an @ somewhere in the middle. In fact, this actually passes on just the @ character, which is not an email address, but hopefully no one's using it. But the people at Superhuman learned that the email spec, or the email address spec, allows for @ symbols to appear in the first part of the email address if they are surrounded by quotation marks. And so they thought they might try and handle that. I think that's a bad idea because no one's ever used an email address with an @ symbol in quotation marks in the first part of their email address. And if they do, they shouldn't be allowed to email people. But it's what the spec says, and Superhuman decided to go after it using this updated regular expression. So they just changed the first part before that @ that's being matched. And they said, okay, now we're looking for either a quotation mark, a whole bunch of things that are not a quotation mark, and then another quotation mark, or anything that's not an @ symbol. Seems like a good idea until it turns out that quotation marks are also not @ symbols. And so this disjunct, this or kind of clause overlaps. These quotation marks can appear on both sides, especially if there's not an @ symbol involved. That's bad. We can go and have a look at that in the regex timer here. I've got this as an example here. And if you just use a string that uses a whole bunch of quotation marks, it matches on both sides of that or, matches on both sides of that disjunct, and allows the results to take several seconds in this case, 7.3 seconds. And if you add another quotation mark, it might do a weird caching thing. It might go, yes, yeah. Chrome is good at this. Interestingly enough, Firefox will actually fail after 4 or 5 seconds of trying to do a regex, regardless of what happens. And Safari has even better caching than this, or better kind of heuristics to tell. But you can get some interesting results out of Chrome when doing this. And so, because these quotation marks overlap with things that are not an @ symbol, we get multiple ways to match a quotation mark in a string. That caused UI lockups for Superhuman. Next up is Zod. Zod is a library to bring runtime type checking to JavaScript. It works very well with TypeScript. TypeScript does your build time, Zod can do your runtime type checking. But Zod adds extra things on top of type check, so it doesn't just check whether thing's a string. You can check if that thing is an email, if that string is an email. And this was the regular expression that they used to check that. This one's a bit more complicated, as you can see. What we have is sort of A to Z 0 to 9, so characters, numbers, underscore, plus, and dash, 1 or more times, followed by 0 or more dot characters. So this is a subdomainy kind of thing again. And this whole group can then be looked at 0 or more times. So question mark is 0 or 1, star is 0 or more. So this whole thing can be 0 or more times. And then eventually you have just characters, numbers, underscore, plus, minus, and then a symbol at the end. So we're saying there can't be a dot before the @. That's effectively what's happening here. How is this a problem? Well, let's break this first part down. It lies in the first part of the regular expression here. And this slash dot question mark means a literal dot character, literal period character, 0 or 1 time. But because it could be 0 times, that's like in the visualization, we can just skip over this. We can ignore it. And so if we take out that dot, take out that slash dot question mark, we get this little chunk of regex at the bottom here. And the problem here is this overlap. We've now got 1 or more times and the whole group 0 or more times. But that is just a big overlap. It's just basically saying we can have this group of characters any number of times in any kind of way. And that causes the exact same problem again that we saw with the Cloudflare one, with the dot stars. This is not dot stars, this is plus and a star, but it's causing the same issue where as you go through the string trying to match things, you can make many different combinations, many different permutations of the letters that match the regular expression, get matched by this regular expression. Overlaps like this are an absolute nightmare. So how do we fix it? What do we do about it? Well, first up, we have to look out for those overlaps, those nested overlaps, nested qualifiers. Anything like an overlapping disjunction. This is a simpler example, A or A and B. If you have an A, it gets matched on either side of that, even though they look like different things. And then if you add a plus to it, it happens as many times. Consecutive patterns. So there's either overlapping patterns like that plus and then a star on the outside of the group, or which kind of count with those overlapping disjunctions as well. Or there's consecutive patterns like dot star, dot plus would be the same. Any kind of thing like that. Those consecutive patterns are just, especially with the dot, with the global kind of matching anything character, absolutely no. Hidden consecutive patterns are also an issue. That's the case where if we want to break our regular expression down, removing those kind of optional matches, we end up with something like a consecutive pattern or an overlapping disjunct. And that's the case like this, where the equals has question mark. Question mark just means 0 or 1 time. We can remove that and say it's just, imagine it's 0 times. Now we can get now we get the consecutive pattern back, and we're in trouble again. So refactoring those kind of things out is a good idea. How could we do this? So in the node fetch example, we had an overlap here of the catch-all character, the dot character, and the period, the literal dot, within that list. And so what we could do to fix this is to say, okay, instead of any character that's not a period, any character that is not a period 1 or more times, and then a period. And that way they don't overlap. We stop, that overlap of things, and we stop giving the regular expression engine multiple ways to match. It's a great way to fix it. It does make it look a bit more complicated, though. If we wanted to fix that addition to Superhuman, in this case, we had the problem that the @ symbol, or not an @ symbol, matches a quotation mark. And so we can add to this kind of not section by saying, if we're not an @ symbol and we're not a quotation mark, that stops the overlap and we stop the problem. Another way to deal with this is to avoid regular expressions at all. If you think back to node fetch, we were actually testing whether a URL host was localhost or a subdomain of localhost. And so that means it either is the literal string localhost, or it will have some characters before it and then a dot and then localhost. And that's what the regular expression was trying to say, but it got it wrong. This is actually the way it did get fixed in the open source library. What we can do is we just check if it's localhost or check if it ends with .localhost. And that does the same thing without worrying about confusing regular expressions and overlapping matching. And one final alternative is to use a different engine, if you're on the server side at least. You could install RE2, that is a Google-built regular expression engine that doesn't have backtracking. And so you can add that, and there are node bindings to that as well. And that does end up dealing with regular expressions slightly differently, but does not fall to any of these issues. And there are other languages, I think like Rust and Go, that use non-backtracking regular expression engines. And finally, how to spot these issues. You might be now, or hopefully you do have a slight worry that there's a regular expression inside one of your applications, one of your projects, that might be subject to one of these issues. And so you want to know how to spot them. Well, here's a bunch of tools that you might want to use. regex.rip is just a website you can test regular expressions against. It was built by the people from Superhuman after they realized what they'd done. Recheck is also an online way of checking regular expressions. SonarCube is a full project scanner that includes checking for regular expression backtracking, catastrophic backtracking within it. If you're using ESLint, then you can add a couple of plugins which will help out. The ESLint plugin ReDoS is the same actual engine that's used in that recheck project. An ESLint plugin regex is another one. Both of those might add, they actually add some time to your running of ESLint, so you might not want to be running it kind of in development, but maybe as part of your CI server. And then finally, there's regex timer if you want to play around with seeing if you can make regular expressions that take a long time to evaluate. All of these links are in the slides, but they're also in this blog post as well, in which I went into greater depth on this stuff and the other kind of backtracking that can cause issues as well. This link will be shared out as well. There's a QR code there if you want to scan it really quickly, because I'm going to move on now and say thank you so much for having me, Extreme.js. This regular expressions are an absolute nightmare when you actually dig into them, so I'd say avoid them first, but know the dangers that you might have as well. Again, my name's Nash. I'm a developer relations engineer at DataStax. Go check out the DataStax platform if you're building with AI or if you're interested at all. Check out these QR codes if you want the slides, or if you want to go check out DataStax and AstraDB. Otherwise, enjoy the rest of the conference, and thank you so much.